From 35,000 feet, the Kansas plains look like a game board someone abandoned. Miles of brown and tan squares, flat and wind-scoured, the kind of land that breaks men who try to farm it without water. But scattered across that grid, at wide intervals, you see something that doesn't belong. Green circles. Perfect circles, each one roughly a mile across, sitting in that dry soil like something dropped there from orbit. What you're looking at is a single machine. One pipeline on wheels, rotating slowly around a fixed center point, covering 500 acres of cropland with exactly the amount of water the soil needs, delivered close to the root zone, with almost nothing wasted to wind or sun. Most people picture irrigation as something simple, a pump, some pipes, maybe workers pulling hoses. Or they picture the old way, flood irrigation, where you open a head gate and let water sheet across the field, and hope it reaches the far end before it soaks away or evaporates off the surface. That method loses somewhere between 30 and 40% of every gallon pumped. In a dry state in a dry year, that's not an efficiency problem. It's a slow agricultural death. The center pivot doesn't work like any of that. It carries water from a fixed center point outward to the last nozzle at the end of a half-mile arm, and it does this while the entire arm rotates, completing one full circle every few hours or every few days, depending on what the crop requires. By the time you understand why the outer end of that arm has to move faster than the inner end, how the system keeps every section of a half-mile pipeline at the same working pressure, and what actually happens when one tower stops while the others keep going, you'll know why this machine changed the American West more durably than almost anything else built in the 20th century. 500 acres sounds large. It doesn't feel large until you put something beside it. Central Park in New York City covers 843 acres. One center pivot system on a half-mile radius irrigates more than half of that. A regulation football field, end zones included, is about 1.3 acres. To walk the full outer edge of a single irrigated circle, the perimeter traced by the end of a half-mile pivot arm, you'd cover just over 3 miles of ground. And that outer section of pipe has to travel those 3 miles in the same time it takes the innermost section to crawl a few hundred yards around the center point. That's the first mechanical problem the design has to solve, and it's not obvious until you think it through. A rigid arm rotating around a fixed pivot doesn't move at uniform speed. The intersections barely move, while the outer end has to cover a much larger arc in the same period. On a standard half-mile system, the last drive tower might be moving 15 to 20 times faster across the soil than the first tower near the center. If every section drove at the same pace, the outer end would fall behind, and the pipeline would buckle. The engineering solution is hidden inside each of the towers that support the arm, and it took most of the 1950s and 1960s to get right. A center pivot system has 3 main parts: the center pivot point, the pipeline, and the drive towers. The pivot point is a stationary steel collar set into a concrete pad at the center of the field. Water enters the system there, from a well, a canal, or a pump house, typically at a pressure between 30 and 60 pounds per square inch. That pressure window is the operating envelope for the entire machine. Drop below the lower threshold and the nozzles at the far end stop atomizing water properly, producing large droplets that compact the soil surface instead of soaking in. Exceed the upper threshold and the spans near the center over-apply water and erode the seedbed. The whole system is engineered around that range. The pipeline extends outward from the pivot collar in sections called spans. Each span runs between 180 and 250 feet long, depending on the model and the terrain. A half-mile system might have 6 to 8 spans. The pipe itself is galvanized steel, 6 to 8 inches in diameter near the center where it carries the full volume, reducing as water branches off toward the nozzles along each span. Every span sits in the cradle of an A-frame drive tower, 2 large rubber-tired wheels on a steel frame powered by a small electric motor. The drive motors don't all run simultaneously. Each tower's motor is controlled by a percent timer located in the center control panel. The timer runs each motor for a set percentage of every 60-second cycle. The outermost tower, which has to cover the most ground per revolution, runs the longest. A tower halfway out the arm runs for less of every minute. The inner tower closest to the pivot runs for the least. The whole arm bends slightly at each tower junction as the faster towers pull ahead and the slower ones catch up. But it never kinks, because the timing keeps every section moving in the same controlled rhythm. Water reaches the crop through drop nozzles, flexible rubber tubes hanging down from the main pipeline, placing the spray head a few feet above the plant canopy. Old-style impact sprinklers threw water 15 to 20 feet into the air, where wind and summer heat stripped away a quarter or more of what was pumped. Drop nozzles eliminate most of that loss. The water exits close to the surface in a pattern calibrated to the row spacing below and soaks into the soil rather than drifting downwind. At the far end of the arm, the last tower carries one additional component: an end gun. This is a large trajectory sprinkler that fires outward when the pivot reaches the corners of a square field, throwing water another 60 to 80 feet beyond the end of the arm. Even with the end gun running, a square field has corners that a circular machine can't reach. Those dry triangles at each corner, typically about 3% of the total field area, are either planted with dryland crops, left in grass, or equipped with a corner arm system, a jointed extension that unfolds as the pivot approaches each corner and folds back as it passes. Corner arms work, but they add mechanical complexity and cost. Most operations accept the dry corners. The machine Frank Zybach built in a Colorado field in the late 1940s looked nothing like what runs today. Zybach was a farmer and a mechanic, largely self-taught, who had watched flood irrigation fail on dry land ground for years and believed there was a way to make the water move itself. His prototype used the water pressure from the pipeline itself to power small air-driven motors at each tower. The whole assembly was hand-fabricated from steel stock he machined in his own shop. It broke down constantly. The alignment was never quite right, but it rotated and it irrigated, and Zybach knew the principle was sound. He filed for a patent in 1948. The U.S. Patent Office issued it on July 8, 1952. Patent number 2,604,359. The description ran to several densely technical pages. The basic claim was simple: a water distribution system that moves itself in a circle around a fixed water source driven by the pressure of the water supply. Almost nobody in agriculture paid attention. Zybach spent the next several years building machines by hand and selling them directly to farmers, mostly in Nebraska and Colorado. The early installations required near constant attention. Towers lost alignment, motors failed, the pipeline leaked at the joints. Zybach repaired them himself, often driving hours to reach a machine that had stopped working overnight. In 1954, a businessman and engineer named A.E. Trowbridge saw one of Zybach's machines running in a Nebraska field and understood what it could become. Trowbridge bought the patent rights for roughly $50,000, a substantial sum for a farm implement at the time, a reasonable price for a mechanism that was still mostly breaking down in the field. He connected with a steel fabrication company in Valley, Nebraska, called Valmont Industries. Valmont engineers switched Zybach's air-driven tower motors to standard electric motors, engineered standardized span lengths, refined the joint designs to stop the leaks, and began manufacturing the system commercially in the mid-1950s. The adoption curve was slow at first, then nearly vertical. In 1960, there were a few hundred center pivot systems operating in the United States, mostly in Nebraska. By 1970, there were roughly 4,000. By 1980, the number had passed 100,000. By that point, the sandhills of Nebraska, sandy, wind-deposited soil that was considered unfarmable for a century because it couldn't hold flood-irrigated water, had been converted into some of the most productive corn ground in the country. The pivot system worked precisely because it applied small amounts of water frequently, which sandy soil absorbs without runoff. The ground that couldn't be farmed was now growing 200-bushel corn. Frank Zybach died in 1980, the same year the machine he invented crossed the 100,000-unit threshold. The $50,000 he had accepted for his patent rights would have been reasonable for almost any other agricultural implement. For this one, it was the worst deal in American farming history. The industry his invention created now generates several $billion in annual revenue worldwide. Zeibach left no financial stake in any of it. A center pivot running well is close to invisible. The machine turns, the crop gets water, the yield comes in at harvest. The failures, when they happen, are not invisible at all. The most common single-point failure is a stuck tower. Each drive tower operates independently. If a motor burns out, a wheel sinks into wet soil after a heavy rain, or a drive shaft shears, that tower stops moving while the rest of the arm keeps going. The pipeline, designed to flex slightly at each tower junction, flexes too far. If the operator doesn't notice within a few hours, the arm can kink at the stop tower badly enough to damage the structural steel of the span. In serious cases, the downstream section breaks free and swings, several tons of steel pipe, unsupported, moving in an arc across the field. Machines have been destroyed this way. Crops under the free-swinging section are gone. Pressure failure works differently but costs just as much. If the center pivot loses supply pressure in the middle of July, a pump failure, a power outage, a plugged inlet screen, the dropped nozzles stop delivering water. Corn in the pollination window, when temperatures are over 95 degrees, can suffer measurable yield loss from a gap as short as 12 hours. A 24-hour outage at the wrong growth stage can cut yield on a 500-acre field by 20 to 30%. On a commodity crop, that's the difference between a profitable year and a loss. The slowest failure mode doesn't happen to a machine at all. It happens to the geology underneath it. Most center pivot systems in the Central Plains pull water from the Ogallala Aquifer, a massive underground water reserve that extends beneath parts of 8 states: South Dakota, Wyoming, Nebraska, Colorado, Kansas, Oklahoma, New Mexico, and Texas. The aquifer formed over millions of years as sediment from the Rocky Mountains eroded eastward, trapping ancient groundwater in a vast permeable layer of gravel and sand. At its thickest in parts of western Nebraska, the saturated zone extends more than 1,000 feet deep. In the Texas Panhandle, in some places, it's less than 30 feet. The Ogallala recharges slowly. The natural inflow rate, averaged across the aquifer, is roughly half an inch of water equivalent per year. The extraction rate since large-scale irrigation began in the 1950s has been orders of magnitude higher than that. In some counties in western Kansas, the water table has dropped more than 150 feet since 1960. Wells that reached water at 30 feet in 1955 now have to be drilled 200 feet down. Pumping costs that were manageable a generation ago have tripled in some areas because the pump is lifting water from twice the depth. There are working farms in the Texas Panhandle where the well production rate has fallen below the minimum flow that the pivot system requires to operate. The machine is still there, the motor still runs, but there isn't enough water coming up the well to keep the pipeline full. Farmers in those areas are making a set of decisions that have no good answers: reduce the irrigated acreage, switch to dryland crops that yield less, or sell and move on. No mechanical improvement closes a geology gap. The aquifer doesn't care how efficient the nozzles are. The person responsible for a center pivot on a working farm today is usually not a specialist. On most operations, it's the farmer or a farm manager who oversees multiple fields at once. Running a large pivot in the 1970s meant driving to the field twice a day. You checked tower alignment by eye, walking the length of the arm looking for sections that had drifted off the track left by the previous pass. You checked pressure at the pivot point with a gauge bolted to the supply pipe. You kept a handwritten log of run hours and estimated water applied per acre, cross-referenced against your own notes on rainfall and crop growth stage. Modern pivot panels have cellular-connected remote monitoring units that text the operator if a tower stops, if pressure drops below a set threshold, or if the system shuts down at the center pivot. Some operations run all their pivots from a tablet, adjusting run speeds and checking alignment maps from the house. The largest irrigated operations in Nebraska or Colorado might have 8 to 12 pivots running simultaneously on a single management unit. A single manager can watch all of them without leaving the office. What doesn't change is the physical knowledge required to run these systems well. Someone has to walk the rows after every pivot pass and check whether the drop nozzles are actually hitting the ground where the soil sensors say it needs water. Clogged nozzles create strips of dry ground that show up at harvest as yield loss. Someone has to pull soil cores periodically and verify that water applied at the surface is reaching the root zone and not sitting above a compacted pan 2 feet down. Someone has to understand what the well pump performance curve looks like this year compared to 3 years ago, because a declining curve means the aquifer below is dropping. The people who run these systems effectively tend to have a combination of mechanical instinct, agronomic judgment, and financial discipline that's hard to find together in any profession. A half-mile center pivot installation costs between $80,000 and $150,000 fully installed. Annual energy costs for pumping from a depth of 150 to 200 feet through a full irrigation season often run $25,000 to $40,000 depending on crop requirements and power rates. Getting the system wrong, over-applying water to soils that don't need it, under-irrigating during a heat event, ignoring a declining tower alignment, costs real money at harvest. These are not abstract decisions. The most significant engineering shift happening in center pivot irrigation right now is variable rate application. A traditional system applies water at a uniform rate across the entire arc of its rotation. Every point under the arm gets the same amount per pass, regardless of what the soil beneath actually needs. But soil is not uniform across 500 acres. A single field may have sandy loam at one end that drains fast and heavy clay at the other end that holds water for days. Applying the same rate to both means either overwatering the clay or underwatering the sand, no matter what rate you choose. Variable rate irrigation systems use GPS coordinates combined with soil type maps built from electromagnetic conductivity surveys and multi-year yield data. As the pivot arm rotates, a controller opens and closes individual nozzle groups to match the application rate to the soil map underneath. The sandy section gets twice the water, the heavy ground section gets half. The result, over a full season, is a more uniform crop canopy and a measurably lower total water use per acre, typically 10 to 20% less than a uniform rate system managing the same crop on the same field. Some of the more advanced installations now integrate wireless soil moisture sensors buried at multiple depths across the field, feeding data in real time to software that adjusts the pivot run schedule automatically. The system knows which zone is still carrying adequate moisture from last week's rain. It skips a pass over that zone and adds another pass over the section that's drying faster because the soil texture is lighter. The operator reviews the recommendation and approves it or overrides it based on a weather forecast the software doesn't have yet. None of this eliminates the water problem. Efficiency improvements extend the operational life of the aquifer by reducing waste, but they don't recharge it. A 15% reduction in annual water use buys time. In some counties where the water table is dropping 2 to 3 feet per year, that additional time may not be enough to matter. The math there is not encouraging. What Zybach built in a Colorado field was, at its core, a solution to a simple mechanical problem: how to move water across a large piece of land without requiring people to move it. The answer was a pipeline that moved itself, driven by the pressure of the water supply turning in a circle. What that answer became is the green circle you see from 35,000 feet, the signature of one machine, turning slowly in the heat, converting dry soil into cropland one slow revolution at a time. The machines get smarter and more precise with every generation. The aquifer they draw from gets a little smaller. Whether the efficiency gains stay ahead of the depletion rate is the question that a generation of Great Plains farmers is living with right now, often without a clean answer. If you want to go deeper into the machines that built modern agriculture, how they work under the surface, how they've held up over decades, and what the people who run them actually know. There's more here. This is where the explanation usually stops. It doesn't have to.